presentation on hockey pucks, and my name's hockeypuck. So some motivations behind this are pucks are shot at impressive speeds at and above 90 miles an hour. This is accomplished using hockey sticks with varying curves on each of their blades. The curves that I'm talking about are on the right-hand side here, from a slight curve to a more drastic curve seen on the left. And as pucks are shot, this curve induces a rotational velocity on the puck. An increasing curve will increase the rotational velocity. Well, how does this rotational velocity affect puck flight? Can a puck's flight be characterized by the Magnus effect? And the setup for this system is a 1 foot by 5 foot by 1 foot flow field, with the 5 foot being the depth of this flow field. Now, a standard hockey puck is 3 inches by 1 inches, and it was placed at the center of the flow field. The puck was given a surface mesh and prism layer of 5 layers that grew in size as it projected away from the puck, where the minimum cell of this prism layer was 0.1 inches and the maximum cell over the entire mesh was 0.25 inches. And the final mesh count resulted in 2.3 million cells. The meshes can be seen below. So some boundary and initial conditions for this setup are that the inlet has an incoming air velocity of 90 miles an hour or 132 feet per second. The outlet has a pressure outlet of 0 psi, and the sidewalls have a symmetry plane which allow flow inside the system. Now the puck is set up to be a wall boundary with rotation added, where the first case has 0 rotation, a second case has 118 radians per second of rotation, and a third case, the high-speed case, is set to be 1500 radians per second. Now initially this entire system has 0 velocity and is set to be the boundary conditions at the first time step. And this results in some noise in the first couple iterations. Looking further, the simulation parameters are air was used as the fluid, and a K-epsilon turbulence model and RANS models were used, with a time step of 0.1 seconds and a solution time for the final solution at 2.5 seconds. The inner iteration count was 15 for each time step. Now the case 1 results where 0 rotation is present can be seen here, and this is a view from the puck from above. As you can see, the velocity wake behind the puck is almost directly in the middle of the puck, behind it. Going further to case 2 where rotational velocity is added at 118 radians per second, or 15 feet per second at the radius, can be seen. Now this one is almost identical, although there is a slight shift upward from the view of that wake behind the puck. Case 3, on the other hand, which has a high-speed rotation of 1.5 times the incoming velocity, shows that the wake is highly shifted upwards, and this is affected due solely to the rotational velocity. Now some notable results and conclusions are that an increase in rotational velocity causes the wake to shift towards the top of the velocity scene. A low pressure zone occurs at the bottom side of the puck, causing the puck to drift in that direction over time, which can be seen in the pressure plots located at the bottom left-hand side of the figures here. And the result is consistent with the Magnus effect for a spinning cylinder, which is reinforced by that low pressure in the 1500 radians per second figure seen in the bottom left-hand side of the view, where the low pressure is located at the bottom edge of the puck and the lower speed shows low pressure on either side of the puck. The right-hand figures all show velocity, which should be the opposite of what we see in the pressure profiles, and that holds consistent. Now, a real-world example of this entire setup can be seen in this video by Dude Perfect, where they shoot pucks at varying distances at varying targets. For this case, they'll be shooting it at a basketball hoop from a long ways, which shows more drastically the Magnus effect. So, zooming forward here, take a look at what we need to. And watch as the puck drifts left over time. As you can see, it drifts left. Thanks for watching and have a good day.